Hello, welcome back to the third week of the Jerusalem Science Contest. Today we'll be looking at Chapter 6 and Chapter 8 in your textbook. Unfortunately, we're not able to cover everything, so I chose to bypass Chapter 5, but I strongly suggest that you read it nevertheless. This is the chapter having to do with optical and radio telescopes, and it's an interesting chapter, and you should get a lot of information out of it. I've also eliminated Chapter 7, which is actually the study of our own planet, the Earth. Again, I think it's important for you to look at that because a lot of what we know about the solar system, for instance, which is one of the things that we're going to be talking about today, a lot of the techniques that were developed were also developed in order to be able to study our own planet. So I think, again, it's an important chapter. Nevertheless, as I said, we're going to have to eliminate those two chapters, and I think there are some other chapters later on that we're also going to bypass. But I'd like to begin with Chapter 6, which is the solar system. The things that we know about the planets today, and we know some of these things from first-hand information, because in terms of of the kinds of measurements that we would like to make regarding the objects in our solar system, one of the things that we want to know is how far they are from the sun, which also enables us to be able to calculate how far they are from us at any given point in time. So we want to be able to measure their orbital semi-major axis, and we can use Kepler's laws, as we've already seen, to do that. The other thing that we can do with some objects is we can actually use radar ranging in order to find their distance from the Earth. So we can actually bounce a radar image off of a distant object, and by determining how long it takes for that signal to return to us, we can get a pretty good estimate of its distance. We could also use lasers for that purpose, and that's particularly useful for measuring the distance to the moon. The radius of a planet or any other object can be found just by using geometry or perhaps trigonometry if we know its angular size and we know how far away it is. So, for instance, we could use, this is the object, and we know its angular size. So if you're here and you're looking up here, and of course these angles are greatly exaggerated that I'm drawing here, but we could actually find the angle, and we look at the total angle, which is from here to here, but then we can make a right triangle out of this if we know, for instance, the radius of the planet, and if we know any one of these distances, then we can obviously find the radius. But if we know even one of these two distances, and we know this angle, so we know what the angular displacement is here, we can actually use trigonometry to find the radius. So if we're using, for instance, let's say we knew that from here to a point which is in the center of the planet, we knew what the distance here was, and we'll call that x. And then we know that the distance here, we know the angle here, so we can say that the tangent of theta is equal to the radius divided by x, and it's a y divided by x type of relationship. So if we take the tangent, the radius divided by x, and that gives us the tangent, then if we want to find the radius is just going to be x, that is the distance in this direction, times the tangent of the angle theta. And that's something that we can get we can just pull this right off of a calculator, or if we don't have a calculator, we can look up that value for that particular angle and then just multiply it by x, and that would give us the radius of the planet. So all we really need to be able to do there is to measure. We're assuming we already have the distance to the planet. So now what we're doing is we're merely looking at the angular size of the planet. The other thing that we want to look at is the mass of the planet, and of course we can get the mass just by using Newton's equation, F equals g m1 m2 over r squared. So this works particularly well if the planet itself happens to have moons. So we can look at the planet and one of its moons and then be able to do that. So for planets like Mercury and Venus that don't have moons, it's a little bit harder but they nevertheless still interact with other objects in the solar system and cause a little bit of a wobble in the orbit of those objects. So you can still actually get the mass of these planets in that way as well. So we've got mass, we've got the radius, the rotational period is something that we would just do by visual observation. You know, basically we look at some surface feature. This was something that could even have been done in Galileo's time. He could have looked at some feature on the surface and then seen how long it would take for that, you know, if the object is rotating, see how long it takes for that feature to appear a second time after it's spun around once. So that's how we get the rotational period. The average density of a planet or any other object. You know, the density is just the mass divided by the volume. So if we assume the planet is a sphere and we know its radius, we know that the volume is going to be equal to 4/3 pi r cubed. So if we have the radius, we now have the volume, and the mass, as I said, we've gotten the mass from this equation then, so we can calculate the average density of the planet in that way. Okay, thing is that kind of an interesting thing is that if we could move outside of the solar system, we've got the sun in the center and all the planets orbiting the sun. And if we moved outside, or if we were able to move so that we were looking at the planets along this plane, the plane of the board, you would actually see the sun here in the middle, and you would see all the planets would be very, very close. If you look along the line of the ecliptic, they would all follow very, very closely along the line of the ecliptic. There'd be a little bit of variation here. You get the greatest variation from Mercury, which actually lies outside the ecliptic by about 7 degrees. And I've greatly exaggerated that, so it's not, this is a lot more than 7 degrees. But you'd have a little bit of deviation from Mercury, but all the other ones would pretty much run right along the ecliptic. Well, we can divide the planets up. This is another thing. So we used to have 9 planets now. The way we're classifying these objects, we only have 8. The former planet, Pluto, has now been relegated to the category of what we call a planetoid. And there are a number of reasons for this, and we'll discuss a few of them today. But if we look at the Earth and the other 7 planets, we're going to find that the inner planets, that is the planets up to the orbit of Mars, are of one type. And then when we go beyond Mars, we're going to get a second type of planet. So we have the Sun, and then we've got Mercury, and then Venus, and then the Earth. And I'm not really drawing this to scale at all, but Venus, the Earth, Mars. I'm not going to continue to draw all this. I'm going to run off the board. But then we have, then there is an area where there may, perhaps at one point in time, there may have actually been a planet that was destroyed, but now there's a lot of debris in there, and it would sort of be the next point along here, sometimes referred to as the asteroid belt. And then we have, I should have really made this a lot smaller, but then we have Jupiter, Saturn, Uranus, and Neptune. So these are the outer planets. So with regard to the inner planets, Mercury, Venus, Earth, and Mars, and what we're going to be looking at today is Mercury, and we're also going to compare it with our moon, which happens to be somewhat similar in terms of its structure. In terms of the inner planets, what can we say about them? With the exception of Venus and Mercury, the inner planets have moons. We have 1, Mars has 2. All the outer planets, on the other hand, every one of them has multiple moons. So only Mercury and Venus do not have a moon. The other thing is that the densities, we talked about densities, we're going to find that the densities of the inner planets are much greater than the densities of the outer planets. But the physical size of the inner planets is much smaller. That is, the radii of the inner planets is much smaller than the radii of the outer planets. And all the outer planets, and this wasn't known until maybe the last, certainly if we went back 20 years ago, I don't think it was known. But I don't remember exactly when these things were discovered, but it's probably back, maybe back sometime in the 90s. If we went back to the 80s, you would have learned that Saturn had rings. I don't know whether Jupiter's rings have been found or not, but we now know that Uranus and Neptune have rings. So all of the outer planets, what we call gas giants, they all have rings, and none of the inner planets have rings. It's another interesting difference between them. So in terms of the inner planets, the Earth and Mars both have 24-hour rotations. So they both rotate about their axis. That is, a Martian day is 24 hours long, just like an Earth day is 24 hours long. But Mercury and Venus rotate much more slowly. Mercury's rotational period is 59 days, so one mercurial day would be 59 Earth days long. And all the planets are rotating in the same direction that the Sun is rotating on its axis. So that if the Sun is rotating this way, then all the planets would be rotating in the same direction. With the exception of Venus. Venus actually has a retrograde rotation. It's rotating in the opposite direction of the other planets. It takes 59 days for Mercury to make a revolution around its axis, and Venus is much longer, about 243 days. So that's maybe, I don't know, 2/3 of a year, of an Earth year, for Venus to make one complete rotation around its axis. And we couldn't see Venus from the Earth. All we see is, because there's a very dense cloud cover, so it wasn't until some of the spacecraft have actually gotten close to Venus that we've been able to look at the surface, that we've been able to learn a lot more about Venus as well. And in terms of magnetic field, of the inner planets, only the Earth and Mercury have magnetic field. So Venus and Mars do not have any detectable magnetic field. There have been a number of spacecraft missions that have been sent to these planets, some of which have actually landed on the planet, and in other cases they were just flybys. Some of the earliest things, after the Apollo 11 landed on the moon, the man mission landed on the moon on July 20th of 1969. At that point in time, in the early 70s, there was a lot of activity going on, and there were a lot of missions that were launched to examine the rest of the solar system. So in 1974 and 75, we had the Mariner 10, which actually flew by Mercury and photographed about 45% of the surface of Mercury. And later, a little bit later on, there was another flyby by the Messenger spacecraft, and that actually flew by in 2008 and 2009. I mean, it was quite a bit later, but that actually photographed 90% of the surface. And of course, since we're looking at more recent technology, and that the Messenger was launched in 2004. So we're looking at something that is a 30-year more recent technology. So the visual images that we got from Mercury were much better from the Messenger than they were from the Mariner. And both of these things used this kind of slingshot effect employed, so that it was possible to speed up the craft. And in the case of the Messenger, this then went on and was able to look at other objects in the solar system. Venus was first. The first missions to Venus were Soviet missions back in the early 60s, and between 1967 and 1978, there were a series of attempts to get to Venus by the Soviets. The Venera 7 through 12, those particular missions were from 1967 to 1975. The earliest one the Venera 7 actually landed on the surface of Venus, and at that time it wasn't understood what the conditions of the surface were like, and so basically it was so hot on the surface that once this thing actually touched down, it was only able to send data back for 23 minutes before basically all of its circuitry just melted and it failed. So it took quite a while before we actually got any more information, and it was the America's Magellan probe that was during the period from 1991 to 94 actually wound up mapping 98% of the surface. So we actually had 98% of Venus mapped out. And since then, we've gotten a lot more information about the planet. Mars, we've investigated Mars as well. There was a flyby in 1965 by the Mariner 4 in 69, Mariner 6 and 7, Mariner 9 in 1971. Was able to do some very, very high resolution mapping of the surface, and was actually able to get 1 kilometer resolution from the distance that it was. And then the Viking in 1976 got much better resolution. Viking 1 and 2 were able to get resolution of surface features. On Mars, they were able to get resolution of surface features up to 100 meters. So that's, again, remember these things hadn't landed, they were still in orbit, so that was pretty good resolution. And then Viking 1 actually did land on July 20th of 1976, and that transmitted back data for a very, very long period. Viking 2 also landed in September of that year, and the Viking 2 failed before Viking 1 did, but Viking 1 continued to send pictures back until November of 1982. So it actually transmitted images for another 6 years. The Mars Pathfinder was in July of 1997, and much more recently, as I'm actually giving you this lecture, it was only less than a week ago that the Curiosity rover actually touched down in the Gale crater on Mars, and this was on August the 6th of this year. But it was really an amazing feat, even though we had landed things before, and I'll have more to say about the rover in coming weeks, because it's only now just beginning to collect data. So we've got a few really wonderful images that have been sent back, but we're going to get some much better images, I think, over the next few weeks. And we'll be talking in the next lecture about Mars, and I'll have a little bit more to say about it at that time, I think. Okay, so the outer planets, Jupiter and Saturn and Uranus and Neptune, these things were actually looked at. Pioneer 10 and 11 in December of 73 and 74. The Voyager, which was one of the earlier shots, in 1977. Voyager 1 looked at Titan, Saturn's moon. Voyager 2 actually got pictures of Uranus and Neptune. I believe those were the only ones that we've actually gotten pictures of. But the Pioneer 10 and 11 missions did a lot of photography of Jupiter. And then Saturn is actually still being investigated by the Cassini-Huygens craft, and that was launched. I don't remember exactly when Cassini was launched. It was a number of years ago, but that's still going to be transmitting data back from Saturn and the moons of Saturn for some time to come.